physically invisible. We started. Let me just quickly check if everything's going fine. Another one. Okay, sorry for that. Cells, J's, speeds. Yes. Hello. Yeah. Okay. It's audible. And I'm not sure if it's clearly audible or not. Anyways, I'll get started. Sorry. And I'm not sure if it's clearly audible. Get started. Sorry. Mhm. Yeah. Okay. So, what we have studied till now, this is going to be just about everything that I've studied till now. So, this whole session is inspired from the content of Pajama Cafe, and this is what I've been studying lately. So, this is actually a night session, and this is a message for Pajama Cafe owner. Uh, if you have any issues, and maybe yes, I have not taken any provision of as such, but this is something that uh, is not for commercial purpose or anything. This is just to understand and evaluate what I've understood. So far now, hold on. Yeah, I think this is much better now. So far I've understood that C is everywhere, from our digital watches to our microwave and even the wipers of our car. So basically, C is not dead. When someone says that C is dead, it's basically not dead. It's just that we have now, like, C is basically in the very bottom layer where it's not really visible, but it is the key component in that particular part, or maybe the embedded system overall. So this everything is given to the author. Reference that author gave is from Brian Kernighan. This was something that I wanted to learn by myself. Maybe if you want, you can go and Google that. I think somewhere over here, this is where we are talking about. And I was not born when C was invented, so my knowledge of its origin and the history is secondhand. Based on the research I did out of curiosity over the past many years, the best resource I stumbled into was a video where Brian Kernighan, one of the inventors of Unix operating systems, talks about the history, C programming language, computer file. C remains an integral part of our technological landscape. Its versatility, performance, and widespread usage across various industries continue to make it a foundational language for software development. So this is something that I took a reference about to learn more about the author later on. And we know that C was developed by Dennis Ritchie at Bell's Lab in 1970, and then inherited several concepts and syntax from predecessors like B and BCPL, which were the previous languages before C that were developed. So it gained traction after the development of Unix operating systems. I'm not going to go deep into the Unix operating system. This is going to be a very just session of what I've understood and what I'm going to learn today. So yeah, gave portability and direct memory access and manual control over hardware resources. Back then, the hardware was not very complex. So C basically gave much more direct access to the memory and to make changes in that memory. So that was the main reason that C is still used in those, very low level programming parts. Introduced structured programming constructs like functions, loops, and conditional statements, if else, right? And promoting code organization. Still widely used in systems programming and OS. Hold on, give me a second. I'll check my. Yeah, I think it's audible. Great. So used to write OS like Windows, macOS, Linux, and now smartphones, tablets, routers. Every day we come across devices that are written in C, and their firmware is written in C language itself. It could be a web router, it could be your car ECU, it could be a microwave, it could be your, let's assume, refrigerators or anything. So, and along with that, these are some of the other features or other places where C is basically used, and other medical devices like pacemakers, which is installed in a patient's heart. You can read about it, Google it, pacemaker, what's pacemaker. You'll get to understand what's a pacemaker. Even I'm really not sure, so yeah. What I know of pacemaker is a device that helps your heart circulate blood or pump blood when it's not capable of pumping blood by itself. So it's a device that helps to control the valves or maybe something like that. And same thing goes for insulin pumps, automotive ECUs. Automotive ECUs are the new thing because almost major of the vehicles that we see are going, you know, mm, are electric vehicles. So they definitely do need an ECU to try to understand. And the key role for ECU in a car is generally to understand like what is the output pressure exhaust, and then try to break down and read from the sensors in the exhaust that oh these are the values and this is the pressure of that particular segment, and based on that only it injects the fuel and the air so that the mixture is proportional and equivalent so that it delivers maximum power. So this is the main calculation that automotive ECUs do. Apart from that, they also do real-time processing in case of emergencies, like if a car crashes, the ABS automatically bursts open and saves the life of the driver. So similarly, game engines like Unity, Unreal engines. So Unity and Unreal Engine is a game development platform, and maybe I think yes, and they do need very thread level based processing so that they can deliver and basically utilize the complete hardware that's there in a laptop to deliver the best output it can. So yeah, and this is the whole diagram wherein there's storage which stores the code and data, and then there's this controller processing unit. Basically, it fetches and executes the code back and forth from storage, and this is the whole computer systems. These are the external peripherals that are connected to the real world and take readings from. You can imagine anything. It could be your washing machine. Washing machine has its own CPU and its own storage to do a particular mode, like spin, drain, and then the buttons are there over their peripherals, wherein we are come in contact and do some actions to you know tell the washing machine to either wash the clothes or dry them. So in the real world, these peripherals are connected to us, and these bridge the gap between the CPU and the actions that we want. So yes, you can try to understand it this way. And just give me a second, I'll just write it down. for my understanding as well, like for later on. As so, there's the storage, and then there's the CPU, right? And then there's this peripherals, which are your knobs, and you also have now chimneys that are controlled with hand gestures. So whenever you see something like that, it's basically it could be any type of sensor that's being used over there, and they take reading, and based on that they control. So anything that comes in contact and have automative way of controlling things, that's where electronics and C comes in. I'm not really sure, but it's computer system. This is the computer system that's there, and then storage basically stores code and data of what's happening and what's not. CPU basically fetches and executes the code, right? And peripherals bridge the gap between digital and real world. So, so this is how these things work over here. Another thing that we're going to come across now is that the above diagram illustrates how the early 1970s engineers used to think about computers while programming and kept the hardware in consideration while programming. So yeah, the early engineers in 1970s, they definitely did not have such thing, and they definitely had to consider the hardware as well while programming the computer systems. So the memory has instructions stored and the CPU fetches from the memory. Based on these instructions, the CPU was able to manipulate, calculate, and influence the external world. So the next thing with what we are going to study, or maybe just give me a second, scroll down for you. Yeah, this is the computer system model. Let's try to understand this. Last time, whatever I was doing, yes, this is a more comprehensive way of studying, wherein this storage given and it is connected to the CPU with address bus. This indicator over here defines multiple. It could be 8-bit, 16-bit, 32-bit, 64-bit. So this indicates that this is a bus, and basically CPU is connected with a single address bus wherein it only fetches in because the address of each register is already defined and program code. It's just fetches it when the data is back and forth. And then there's this CPU, and it has these registers, small registers. It could be latches. I'm not really sure like registers or latches, but let's just Google it for now. Because I don't know, I've lost touch of it. Never mind. I'll again let registers are latches. Not latches. They are composed of multiple latches or flip-flops connected. Okay, so these are basically not latches. These are the constitution of multiple latches. So difference between registers, the flip-flops, and latches. Okay, so yeah, flip-flops are single-bit devices with two stable states, and then we have latches are the same as for flip-flops. Several latches can be combined in parallel to form a register. So yeah, register is something that's made out of say latches. There will be inputs for each bit plus a clock. An 8-bit register used inside a microcontroller would hold a single byte. Yeah, Anyways, moving back onto our topic. So the CPU structure has multiple registers from R0 to Rn, and then we have our arithmetical logical unit, ALU, which computes what logic to perform. And then we have our control unit. So we're going to understand how each of the block is understood over here. So we can see that R1 and R2 are connected to two parts of this ALU. Just give me a second because I'm also making my personal notes in my own copy. So yes, so just file. It's going to help me out anyways. And then this ALU is another connected to the R0. Okay. And then R0 has its own control unit. It's connected to control unit. And then R1 and R2 are given inputs to the ALU. Okay. So this CU is the control unit. ALU is the arithmetic logical unit. And then we have our interest bus. Then we have our data bus. So let's try to read what it says in the text, and let's write down those notes. So this is basically a computer system model. There is a way to think about things, a mental model, so to speak. When it comes to C, you should really think of the CPU, how it computes, works with memory, handles peripherals. A goal for this chapter is to change your frame of reference when it comes to think about computer systems. Figure from no, 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 no. Again, it's important to know C was made to make life easy. Back in 1970s, assembly programming was the way to program CPUs. C was designed to abstract out assembly so engineers could write in English like human readable language, which made life easy and increased productivity. It is thus very important to be able to look at C code and be able to imagine and infer the assembly code it would result into. I should let you in on a secret at this point. In C, every statement is either a math operation, data movement, or a memory operation. So this is what every CPU has an associated instruction set architecture where serves a contrast between the hardware and software engineers. Assembly language allows writing programs using those instructions as a text file, which a separate program called the assembler can then convert into machine code. We'll explore this in great details later chapters. Okay, so basically what it meant was that C was, uh, developed to make lives easier, and back then, okay, so I'll just write it down. Back then, engineers used to code and assembly, and C was developed to make things easier and to code in English like language to help with more productivity. Oh, yeah, everyone wanted them to be efficient. I don't know why, like, everyone wants people to be efficient with multiple things. Never mind. I will like write this over here, and yeah, let's try to understand now what is going on. Okay, so this is basically the load store model now. Okay, So load store model just has an external. Okay, I'll just duplicate this. Yeah, it is a load store model. Okay, so give me a second. Mhm. Now that I have picture, yes. So, load store model. What's a load store model? A simple model of computing system would be that of a CPU connected to some storage, with the ability to fetch instructions and data from it. Shows the central processing unit, general purpose registers such as R0, R12, which is a combination of multiple latches, shown as register file play a crucial role. These registers serve as temporary storage location where the CPU can perform various operations. With the ability to execute operations like addition, subtraction, movement, division, and comparison, and more, the CPU can manipulate data stored within these registers. Moreover, data can be transferred between the general purpose registers and memory over the bus. To achieve this, the CPU floats the desired memory address on the CPU floats the desired memory address to the address bus and reads or writes data through the address bus. When data is transferred from memory to a register, when data is transferred from memory to a register, it is known as load operation, while moving data from a register to memory is referred to as a store operation. The seamless exchange of data between registers and memory allows the CPU to efficiently process information and execute instructions. A figure extends the model to include peripherals. The important thing to notice here is that a peripheral is treated as memory. What this means is reading and writing to the address corresponding the peripheral regions would result in some interaction with real world. The LED, for example, can light up when corresponding peripheral address is written to. Okay, sounds good to me. And okay, great. So basically, what it meant was that the storage connected to the CPU. The register file is basically used for the processing and storing it temporarily so that it does not have to constantly go back and forth. So first thing first, the address bus it's used right to achieve this. Okay, so this will look the desired memory address on the address bus. So the storage has multiple register files similar to like this only, and they have their own addresses. So the address goes there and calls out. Then storage data bus fetches that mm, particular set of instructions and then stores them. So this is called load, right? When data is transferred from memory to a register, it is known as load operation. Okay. hmm Okay. When data is transferred from memory to a register, it is known as load operation. When data is transferred from registers to memory, it is known as store operation. Sounds simple? Great. Okay, and same thing goes for the peripheral as well. You must have seen that it acts like a memory because every time we are like turning it on, the LED remains on, and every time that we are turning it off, the LED automatically goes off. So this is what it means to say the important thing on a peripheral is as memory. What this means is reading and writing to the edges corresponding to the peripheral regions will result in some interaction with the real world. LED, for example, can light up when corresponding peripheral address is written to it. Okay, so now that we have come to storage data instructions, memory is a fundamental component of a computer system, and it operates at the level of individual bits. Each bit is composed of electrical components, elements that represent either the presence or absence of electrical charge. This distinction translates to the binary system. It could be plus 5 volt or minus 5 volt or 0 volts. Basically, something like that. Each bit is composed of electrical charge. This distinction translates to the binary system where the presence of charge corresponds to a 1 or on state while the absence of charge corresponds to a 0 or off state. Assembling these bits, 8 of them form a byte and 4 bytes combine to form a word. So, yeah. Storage, data, and instructions. So, we'll just move on to another part of it. Then we'll duplicate this one. Okay. Mhm. Mhm. Storage. Sorry guys for if in case I am taking a lot of your time because definitely these notes are going to help me out later in the future. So yeah, and we know that each mm, memory operates at the level of individual individual bits wherein each bit is composed of electrical elements that represent either the presence or the absence of electrical charge. Oh. 0 equal to off equal to or let me just this can give me a second. Yeah, or 1 equal to on states, right? And we know that 8 bit is equals to 1 byte, comma 4 byte is equals to 1 word. Combined to form a word, CPU interacts with the memory in chunks rather than accessing individual bits. It can read or write data in units of 1, 2, or 4 bytes depending on the architecture. Direct bit level access is not possible, therefore, the content stored in memory is essentially a collection of bits. How the CPU treats and interprets these bits distinguishes between two crucial concepts: data and instruction. During the execution of load or store instructions, the CPU employs the address bus to transmit a value, a numerical representation that corresponds to an address within the data region of memory. Simultaneously, the data bus establishes a connection with the register file, enabling the transfer of data. Conversely, when the CPU is not performing a load or store operation, the address bus carries a value that corresponds to an address within the code region of memory. In this scenario, the value present on the data bus is interpreted by the CPU as an instruction. initiating the execution of a specific operation or sequence of operation. This differentiation between data and instruction is crucial for the proper functioning of the CPU and execution of desired tasks. Okay, nice. So basically, whenever we are not going load and store, it does a different thing. And whenever we are not doing load and store, it does a different thing. Oh, suppose everything. Hmm. CPU uh, does not doesn't interacts with each bit individually, but in chunks, comma, of one or two or four bytes, depending as per architecture. Okay. Direct bit level access is not possible. Therefore, the content stored in memory is essentially a collection of bits and data and instruction. During the execution of load and store instructions, the CPU employs the address bus to transmit a value, a numerical representation that corresponds to an address within the data region of memory. Simultaneously, the data bus establishes a connection with the register and enabling the transfer of data. Conversely, when the CPU store address within the code region of memory, the value present on the data bus is interpreted by the CPU as an instruction initiating the okay. So basically, when not in load and store mode, the address bus responds to the address of the of that data region, and data bus also establishes connection with the same register file, enabling data and data transfer. Think of it like this, that let's assume if whenever it's in load store mode, it would the address bus would indicate 0x00 and the data bus would read out the data that's written over here. And every time it's not doing certain thing, then it would definitely go to a default setting wherein other instructions are given, something like that. Okay. Okay. So conversely, when not okay, not in load and store mode, the address bus carries a value that corresponds to the address within code region of memory In this in this scenario, the value present on the database is interpreted by the CPU as an instruction. So now I understand about instructions on a much more deeper level. Instructions, modern CPUs utilize instructions that are 32 bits or 4 bytes in width. These instructions are composed of different combinations of on or off states in 32 bits conveying specific tasks to the CPU. Okay, and okay, so let's resume. We'll just move over here. Instructions. Hmm. For instance, these 32-bit can be organized to represent operations such as adding two registers together or moving a value into registers. The CPU can determine the required operations by examining the predefined section of the instruction known as opcode. Let's consider the opcode as okay, opcode is 7 bits wide, spanning from 31 to bit 25. The value of opcode corresponds to a specific operation. In the image, for example, the opcode OX0 denotes an add operation, while OX signifies a move operation. Additional parameters associated with the opcodes are known as operand. Okay, so we are going to understand about opcode now. Opcode, operands. For instance, these will run on specific tasks, operational codes. But they'll define these 31 or represent operations such as adding to registers by moving value into a register. The CPU can determine the required operation by examining a predefined okay, opcode by which CPU determines the operation to take place by examining a predefined section of that opcode. Spanning from 31 to 25. The value of opcode corresponds to a specific operation in the image, the additional parameter associated. Okay. Additional parameter associated with the opcode are known as. Okay, we look at the model of a predecessor to explore it all, understanding such a modeling because C was designed to manipulate such systems. We'll look at each part of this model in some details before starting with the C language. Okay, great. So now that we are into the storage models now, I am going to dedicate this one for now. And yeah, okay, fine, great. Works well for me as of now. Okay, great. So storage model, how does the storage model works? And we want to understand how these latches and everything works. Well, all right. Okay. This chapter, okay, when it comes to reasoning about C programming while debugging, having a mental model of how the data is stored comes in really handy. All of the embedded engineers very naturally understand it. In this chapter, we'll explore how the data may be stored and continue to refer to it in the later how the data is stored, understanding how the data is stored, understanding how the data is stored. You know, okay. Because modern CPUs use solid-state storage, we would only be bothered about the bit implemented using some circuits. CPUs use the presence or absence of voltage on a wire as logic bit, 0 or 1. We explore the possibilities how a bit might be implemented, ways to store, how CPU takes in the presence or absence of voltage on a wire as a logic bit 0 or 1. First of all, let's try to understand ways to store a bit. There are many ways to implement a bit. For our purposes, we will look at two ways of doing so, feedback and charge trapping based. These are the ways in which most modern day storage solution is implemented. So reliable when reasoning about a modern embedded system. Ways to store a bit. Number one, feedback. Okay, let me just make this a toggle list. Turn into a toggle list, and then yes, Control C, Control V, and number two is charge tapping, charge tapping. Great. Okay. Sounds good to me. Oh, yes. Mhm. Hmm. Feedback based. A transistor circuit based implementation of the NOT gate logic. Gate. Truthable logic. Feedback based bit implementation employ a loop mechanism to trap a single value. Consider NOT gate, also called an inverter. If two NOT gates are connected in series, the output of the second one is feedback to the input of the first one. The output of the second one the is feedback to the input of the first. Output always follows the input value. Choose an implementation. Okay, this is what the feedback it meant. The process of storing bits to be traffic logical where it comes reading like feedback based circuits are work as is a power supply that is keeping the NOT gates active. So store enables click, and then there's this one that would go over here, one, zero, and then there's this zero, and then this go one, and then this continuously going to one and zero, one and zero, one and zero. This if we have zero over here, and then we are given one, and then there's this one, and then this is again connected to. So yeah, and this is store enable, and this is read enable, and this is the read line weak inverter. Okay, so when it comes to reading the stored value, an inverter on the read line retrieves the information that was loaded onto the store line. This completes the process of storing and retrieving a bit, employing strong and weak inverters along with full. Okay. Backend is calculating the inverted value and feeding it back to the input. Desired bit value is maintained once the feedback loop is updated to reflect the expected value. The store line can be disconnected. Okay, so something that needs to be understood over here is that okay, the feedback based circuits. This could be RAM, I think, and that is very powerful. Work as long. This is a very volatile memory, as if there is a supply, power supply. Uh-huh. That is keeping the NOT gates active. The storage elements and active digital logic can be assumed to look like so. And okay, so this is the structure that maybe in the future would help me understand this more thoroughly. Okay, yes, works. And then there's this charge trapping that we need to understand now. Okay, trapping charge. It's like a capacitor being used, right? Ah, okay. So, charge storage based technique attempt to trap or store electrical charge and represents absence of it, convey the logical state of -0 or 1. EPROM or flash technology is based on trapping the charge in a MOSFET's gate. Discussion on those would be a complete overkill at the moment. The idea is to load the charge on some sort of capacitor, later read the state of the charge. Such bits are complex in design compared to feedback-based designs. The capacitors can be gate, terminal of a MOSFET, or a literal capacitor, as in case of DRAMs. Okay, charge trapping is used mainly in flash or electrically erasable programmable read. Equal. Hmm. Basically stores the logical value in the form of electrical charges, and sometimes the gates of a MOSFET or virtual capacitor in DRAMs. Okay. Figure shows the charge, storage, and capacitor being loaded with charge and storage being active. Depending on the logic level of the store line, the charge will either be deposited or withdrawn from the capacitor. The read, enable, and read line are essential just to probe the state of the charge and decide on the logical value being stored. And now we're going to start about bit register and register file. What's this? I mean, the whole thing that's been going around and down, down, down. It's so this is the way to store bit register. Oh my God, I am studying it from the very core part of how the things are working now, and it is like breaking my mind from scratch and making me think how on the world with somebody. Yes, the CP model is also there, and now after that, maybe the programmer's model. Okay, so the program counter would come, and then there's this, and then there's this instruction set RISC-V architecture. Okay, so this would actually help me understand it on a much more deeper level now. This book is going to make me uh, set up a virtual lab. Okay, okay, sounds good to me. Okay, okay. Part 2 assembly. Oh, we're going to understand assembly now. Oh my God. Scene enzyme kind. Okay, okay. Launching GDB, assembly language, ISA and assembly program. Uh, okay, okay. Book is very long, anyways. Then we are over here as well. Let's see what's there to learn now. Okay. Uh, mhm. This is a very nice book, anyways, because I didn't understand the C language in like the complete text. Right now, I'm trying to understand the CPU models, memory models, and how these are appropriate, uh, operated, and how do they work actually. Now we have the storage model. So we are in the bit register and register file, feedback based. So let's do one thing. Let's just try to complete this part as of now. Feedback-based storage can be implemented using transistors. This makes life easy, but it is very expensive unless otherwise state explicitly. Assume that all of the storage is implemented using this technology. But a clock feedback circuit is called a D flip-flop, which can be used to store hmm, uh, clock. Okay, I'd rather like okay. So feedback-based storage can be used transistors. Multiple flip-flops can be arranged to store multiple bits of information. They are usually grouped into powers of two. The result of group of bits is referred to as register. There's this D, Q, and then there's this clock. And we can understand about the D flip-flop later on, how it operates, how it's, basically. Sorry. Multiple flip-flops can be arranged to store multiple bits of information. These are usually grouped into powers of two. The result group of bits is referred to as a register. So this is bus of T7-0, right? Enable data in read. Registers can be further combined to make a register file. A register file, as shown in figure, has multiple ports point to connect wires, given address, register number, data in. Can be loaded into the register if write enable is 1, clock signal is transitioning from 0 to 1 unit. bit size, blah blah blah, blah data in, blah blah blah, blah. And when this is memory for all practical purposes, you can assume the memory to be a long registered file shown figure 18. Memory can also allow simultaneous read and write, but we don't really care about the details. Memory is addressable at byte level, so it would be accurate to imagine that memory is an array of registers that are 8-bit wide. Okay, when it comes to storing a bit, there are two main approaches: feedback-based or charge storage-based. For our purposes, we will focus on the feedback-based. The third one, commonly used circuit for this purpose, is the D flip-flop, which can be grouped together to store multiple bits. The collection of D flip-flop is referred to as a register. Okay, and this is something maybe I could just like screenshot and then paste it over there. This would definitely help me out that way because it's too much of writing thing all because I'd like read it then write again. Ha ha ha. So smart of me, right? And no, not really, because that is the big anyways, we are mhm, mhm. Yeah. So this is the whole system that it has there. Okay, so I think I definitely have to write as well. Okay, so मोटा मोटा जो ये बोलना चाह रहा है कि bet is just a deflip top which can be used to bet is bet a clocked feedback circuit is called a deflip flop which can be used to store a single bit. Number two, registers is the collection of these nodes. Registers, on the other hand, multiple flip-flops, multiple flip-flops can be arranged to store multiple bits of information. These are usually arranged, usually grouped in power of 2. Register file is the combination of these. Register file a combination of these registers. Hmm, okay, sounds good to me. Okay, so are you going to understand that the CQ model instruction bit? This is okay. Let's do one thing. Yeah, as of now, we have understood about the memory module very thoroughly and the history of it. And storage modules, yes, and tomorrow we will duplicate and this have CP models. CP models. Yeah, for now, I think this is not just going to be a very long video. So let's end this video for now over here and let's try to understand how we can move ahead. Great. And yes, average view duration, never mind extreme health, poor. I'm not sure how long this video is. And yeah, okay, bye bye. Hasta la vista. Yeah, so the video took around 1 hour, and it's totally fine. I'll cut the snippets and check it out and post it. Great.